Hello everyone. This video tutorial is solution to problem 2.76 of chapter 2 free vibration of single degree of freedom system from book Mechanical Vibration by S.S. Rao 5th edition. Statement of the problem is find the equation of motion of uniform rigid bar OA of length L and mass M shown in figure 2.98. Also find its natural frequency. So the uniform bar or rod, it is supported by three springs. One is the torsional spring of torsional spring stiffness Kt. The other one is a linear spring having stiffness K1. At point A is another linear spring stiffness K2. The bar can be rotated about the pivot point O, and the center of mass of the rod is GCG, and that is in between like that is the center of the rod. So we need to draw its equation of motion, we need to draw its free body diagram. So assuming direction of rotation in clockwise direction as theta here, and that is the direction of rotation. So then one that torsional spring, it will produce a moment which is opposite to the direction of motion, which is kt theta. And then linear displacement of spring K1, I assumed that x1, and linear deflection of spring K2 is x2. So they are in vertical direction. So using s equal to r theta, x1 is equal to its radius of rotation a times by theta, and then x2 is its radius of rotation l times by theta. So the weight of this spring is acting downward direction, but in this case, uh, it is supported by static deflection because two springs are attached here. So the weight of the rod is supported by these two static deflection of the springs. So it is it is cancelled. So we are not going to consider weight in this case. So weight is balanced by static deflection of springs to attain static equilibrium, so we are not going to consider it. So now I need to resolve these forces perpendicular to the rod, and those forces are here. It is K1 x1 cosine theta, and the assumption here is that theta is nearly equal to 0, or theta is small. So as theta is small, so sine theta is nearly equal to theta, and cosine theta is equal to 1. So sine theta nearly equal to theta, and cosine theta is equal to 1. So now Newton's second law of motion can be applied to find sorry equation of motion, so which is sum of all moments is equal to j equivalent theta double dot. In this case, uh, one moment is kt theta, the other one is moment due to that k1 x1 cos theta, which is nearly equal to k1 x, because we are assuming that cos theta equal to 1. So times by its moment arm. So k1 x1 times by a, and that k2 x2, its component will be, it is k1 k2 x2. This component perpendicular to the rod is k2 x2 and cosine of theta. So there are three moments here. So there are three moments here. So I'm going to write. So it is minus kt minus k1x1 into A minus k2x2 into L and j theta j for this rod. So this rod is not rotating. This rod is rotating about point O, and first here moment of inertia of rod having mass m and length L about its center of mass g is jg 1 over 12 ml squared, but it is not rotating about its center of mass, and in that case moment of inertia of mass m having center of mass g and rotating about a point A where AG is equal to D. So it is J A is equal to JG plus MD squared. So it's equal to 1 over 12 M, and the length of the rod here is L, ML squared plus M into D square, and D is the distance between center of mass of the rod, and that is the distance between center of mass of the rod and point of rotation, and that D is D D is equal to L over 2, so that is L over 2 squared. So that is J into theta double dot. So x1 is a theta, so after substituting here, it will become minus k1 a squared theta, and x2 is L theta. So while substituting here L theta, so it will become k2 L squared theta, and a 12th and 1 by 4. 1 over 12 plus 1 by 4, it will become a third ml squared into theta double dot, and then I can rearrange that. So after rearranging it, it will become a third ml squared theta double dot. Kt on the other side will become positive, so I can take a theta as common factor from here. So the coefficient of theta will become kt plus k1 a squared plus k2 l squared, and equation of motion for that will become like J equivalent theta double dot plus kt theta, and in that case natural frequency is whatever is the coefficient of theta divided by the coefficient of theta double dot. So in this case, then the natural frequency of the system will be kt plus k1 a squared plus k2 l squared over a third ml squared under the radical. So that is the natural frequency of this system. Thank you very much for watching.